Hello and welcome to another episode of the Oxford Online Maths Club. My name's James and I'm here to do some mathematics with everyone. How's everyone doing? Good to see you again for this online maths club thing. Hi to George. Oh, there's a bit of lag there. Lag. Is George going to appear on that screen? Have I set that up right? Oh, maybe I've set that up wrong. Oh, I have set that up wrong. There we go. There's George. Hi to George. Hi to Matthew and Raphael, an anonymous person, Maximus, Josh, who's here from the Matt live stream yesterday, Kat, and a new person called Arnelia. Hi Arnelia. Yeah, you can join in. There you are. Welcome to the live stream. Welcome to the club. If people are new here, because they were, so Sally I saw earlier, it's been the open days today and yesterday, so we might have picked up some new people through that. If you're joining us for the first time, hi! This is going to be a bit like the open days, I suppose, but instead of talking about admissions and A-levels and things like that, we're going to talk about maths, because that's what I want to talk about. Hi to Rishi, another anonymous person, Noah, Sad, Ali K, Playhan, someone's taken the username E, which I love. Here it comes. E, Ragnar, Kelly, hello from Anonymous in all caps, another anonymous person with a smiley face. People did a math workshop, those are still on this YouTube channel, so if you check this YouTube channel then you can find out about that math workshop we ran earlier. It's a little bit of sort of sneak preview of the math live stream, I suppose. Math live stream this summer is going to be lots of math questions. Right, let's approve some more chat messages. Someone with a name Tom Lehrer is here, which is quite close to Tom Lehrer, who writes songs. Anyway, Georgia is here. Somebody says mechanics or stats. I think that's a question for you in the audience. Ragnar here likes maths. Column P. B is here again. More excited for some maths. Someone called SV. It's a username I recognise from a math workshop today. B says hello to the newbies, which is nice. It's a very friendly maths club. We just hang out and do some maths together. Kelly's new here. Nice to see you, Kelly. If you're watching on YouTube and you want to join in with this thing, it's very friendly today. Hi everyone. Gabe's new here as well. The math workshop today was the same as same stuff as the stuff yesterday. Sorry, I'm answering the question before it appears on the screen. Yeah, Mac Workshop's same today as yesterday. I ran it twice back to back. I made fewer mistakes the second time round, which is good. If you were here yesterday, you saw me made loads of mistakes. Someone's here from the open day, which is nice. Right. Yeah, I should say, if you want to join in, we're on slido.com/OOMC. That's where we are. Ayana's here from the workshop. Loads of people have come over from the workshop. People have come back from the workshop after seeing that. We did 3 math questions earlier. Oh, I did 2.5 maybe. And yesterday we did the same 2.5 math questions and the 2.5. Yeah, I think it's more people than normal. From open day people as well. Gareth Southgate. Aren't you busy? I feel like you should be busy, Gareth Southgate. Hi. And hi Charlie. Right, okay, great. You've all made me smile. That's fantastic. Here is the plan for today. Coming up, today is all about how to count. I'm going to do some counting. I've had this big exhausting open day today and I just thought we'd do something easy with just a bit of counting. So we're going to learn how to count. It's also going to be an exercise in recycling because I don't usually do this on the Maths Club, but I'm using some slides from a talk that I used to do with people in real life, like face to face. I could see them and stuff. It was ages ago, and I'm now slightly recycling that. I want to see if I can use the thing I did live in the real world in this online thing as well. And I also want to see how it goes when people are joining in all the way through. That's something I really like about live chat, which I'm getting behind with already. Here before the fame, says someone, which is brilliant. Yeah, hi everyone. I want to see with the live chat what it's like when people are actually sort of interrupting me lots and saying things. I really like the way that live chat says stuff. You know, like those live streams with all your favourite live streamers where they join in and say things. We are reusing things, yes. Hopefully reusing things that people haven't seen before, but you know, it's also a topic, so I used to do this talk live. Anyway, let's not talk it down too much. I haven't started yet. Okay, further reading each week is posted on the Maths Club website. maths.ox. Let's read it. maths.ox.act.uk/r/club. On Friday, I post something to do with the previous day's live stream. So at some point on Friday that appears. If you check back at the weekend, you can find sometimes it's a little bit of paragraphs of text of other stuff you might be interested in. Sometimes I find links on the internet for other things to read. Other bits and pieces. Yeah, Maximus has reminded me to say the further reading on Friday. The slides are also here to remind me what to say, which is great. Sam wants to know if I'm a tutor at a college or not. Yeah, I've been... I suppose not quite a tutor. I've been doing some tutorials. Let's put it like that. I've been doing some tutorials for one of the colleges. It's been really good fun. I've been helping out their first years, helping them to learn maths. Aha! Flynn already knows what countability means, which I've put in the YouTube title. Maybe there was a mistake, because now Flynn's told everyone what countability is. Ooh. What A-levels did the further reading do? Brilliant. You see, we've got all these new people, and now you're doing sort of in-jokes. It's not fair, right? So people keep asking what A-levels I did, or what A-levels my guests did. So now, see, I've got to explain the in-jokes now. Okay, right. Great to have you all with us. Let's do some maths. Okay. Let me just check that my next slide is what I think it is. Oh, yeah, okay. So the way this works, it is what I think it is. The way this works is that I need to show you two very boring slides. Two slides with basically nothing interesting on. And then the game is that we try and use that very boring, not interesting maths to get to something interesting. So to try and get from a really boring starting point, nothing interesting there at all, should be really boring, to get to something interesting, to try and build some maths up. I want to try and demonstrate what it's like to have a kind of very small starting points that you then build mathematical theory from. Okay, so first slide and the second slide, both really boring. And in fact, some of the late. Anyway, there's a reason I stopped doing this talk. Anyway, Kat has put some code in chat. I don't know, do I approve this chat message or not? Let's have a think. Sure, there's some code for you all. There we go. And Rebecca's here as well. Cool. Okay, here's the first slide. Very boring. I'm going to start by defining some things. I'm going to explain what some things mean. First thing I want to explain is the notion of things being the same size. Now, this is something that you've probably met before, the idea of things being the same size. I've got a slightly nerdy way of phrasing it. I say that two sets of things, so already I'm using the word set for like a collection of objects or whatever. I say that those are the same size if there's a one-to-one correspondence. One-to-one means for each of these there's one of those, and for each of those there's one of these, between the elements of A and the elements of B. So here I've got a set of apples and I've got a set of bananas, and the one-to-one correspondence is shown by these blue arrows. For each of these is one of those, for each of those there's one of these. Okay. Oh, amazing. People in chat know where this is going. I should say, I know a lot of you watch sort of 3 blue, 1 brown videos, because a lot of you pretend to be 3 blue, 1 brown sometimes, and I know that lots of you have seen things like Vsauce. So most of you have seen, some of you have seen the start of what I'm going to say. Part of the reason I'm doing this is because after the ad break, I want to see how far I can get with this stuff. I want to try and get further than 3 blue, 1 brown or Vsauce or something like that, because I think everyone here is quite keen. I mean, you're watching a maths talk at 5 PM on a Thursday. You could be anywhere right now. Yeah, some of you pretend to be Grant Sanderson too. You could be anywhere, but you're here watching a maths talk, and worse, a boring slide of a maths talk. So I'm going to try and see if I can get further than the Vsauce video that I saw on this. Right, okay. Love seeing people I know in here. Numberphile and VHeart, yeah. People are done. Okay. It's reasons I retired the talk and now recycling it. Okay, so we say things are the same size if for each of these is one of those and for each of those is one of these. Not exciting. Probably you've been looking at these apples and these bananas, and the maths concept that you've got in your head that you're screaming at the TV, it's the concept of 3, that there's something 3 about both of these pictures. And that's also something that I can formalise in my nerdy, boring way by coming up with another word. The word countable is something we say about sets. We say a set is countable if it's the same size as some set of positive whole numbers. So here, this set of apples is countable because it's the same size, there's this one-to-one correspondence, between the set of apples and this set of whole numbers. This is the thing that you learnt to do when you were tiny and you were learning about counting. You line the apples up and you go 1, 2, 3, and what you're doing is making sure that there's a one-to-one correspondence between the set of apples and some set of positive whole numbers. Which, you're checking that the thing is countable. Okay. So this should also not be too, too exciting or weird, right? Because this sort of is the sort of counting that you were doing when you were really tiny, right? And you know this idea, you line them up, the one-to-one correspondence makes sure, this rule for each of these is one of those, and for each of those there's one of these. That makes sure that you don't count anything twice, and you don't give the same number to any two things, right? So it's no good just having a big collection of things and going 1, 1, 1, 1, 1, 1, 1, 1, 1, 1 for all of them. That's no good. And it's also no good having one item that you then give all of the numbers to, and then you look at the next item and think, I've run out of items, apples now. I mean, nobody really makes those mistakes when they're counting apples, but here we go. People are putting definitions of countability in chat, which is very exciting. Maybe I shouldn't have put countability in the title. Oh well, we're getting there. Ragnar likes listable better, listing things, which I quite like as well, I guess. Okay, right. Actually, on to nature. Which apple would you eat? Which of these photos of apples I stole off Google Images would you want? Okay. People are putting interesting. Yeah, are we going to be countable or uncountable? See, the interesting thing about this, I suppose, is that it allows us to have sets that are infinite but also countable. Let me draw you what that might look like. I've realised I have not included the picture I was going to. So an example of an infinite but countable set would be, let's say you've heard the phrase, an apple a day keeps the doctor away. And I've heard that phrase, I want to keep the apple away, I want to keep the doctor away forever. So the thing I'll need to do is I'll need an apple for every day. I'm going to live forever, right? Because the apples make me immortal. The doctors can't get me. They hate this one simple trick. Anyway, so I'll have an apple today, and then my plan is to have an apple tomorrow, and then the day after. And then I'll call this one sort of day 4 or something, and then the next one is going to be day 5, and so on. That's an infinite set of apples. I'll need quite a big collection of apples to pull this off. But on the other hand, it's a really big set of apples. It's infinite, but it's countable because there's a one-to-one bijection, a one-to-one correspondence, sorry. I'm trying not to say bijection. A one-to-one correspondence between the apples and the numbers. The number tells me which apple to eat. I could put little number stickers on them if I wanted to. Can a set have the same number twice? So no, sets have to have different things in. The concept of a set that's got repeats in is called a multi-set, and we're not going to have those today. I am a doctor. Oh no! This is a disaster. Right, okay. They do look like tomatoes. It's not an not an art stream. Yeah, that person talking about infinity a lot. Right, anyway, okay. Right, not an art stream. What are we doing? Oh yeah, okay. So this is a sort of a countable set that's also infinite. Turns out with the live chat I also get distracted a lot more. That's an interesting consequence. There's a sort of mental model that people have for these infinite but countable sets to imagine maybe all of the numbers. And that's like a number line. But to make it a bit more exciting than just imagining a number line, the story that people tell is called Hilbert's Hotel, which I'd like to introduce to you now. There's maybe a chance you've heard of Hilbert's Hotel before. If you have, just chill out for the Hilbert's Hotel section. Chill, you've seen this before, it's fine. If you haven't seen Hilbert's Hotel before, you're going to love this next bit. Right, okay. Here's the idea behind Hilbert's Hotel. It's a very long corridor. So David Hilbert is a mathematician, lived about 100 years ago. He's most famous for coming up with a set of 23 problems that he thought all of mathematicians should focus on. You might have heard of the Millennium Problems, which were set in, well, were collected together in the year 2000. Hilbert's problems were like the original version of that in 1900. Collected together a set of 23 problems that he thought all mathematicians should focus on. 121 years later, we've done some of them, but nowhere near all of them, and some of them are impossible. Right, okay. Yes, that's Sam from the workshop before. I had to do a lesson on this to year 9s. Yeah, I've tried this with year 9s too. It's tricky, isn't it? They don't like it. Right, okay, here's the hotel. Here's the idea. On this side, this is all like the gym and reception and stuff like that. So these are all sort of function rooms. But on the other side, these are the rooms for guests. So as a consequence of this, I've put this photo in, and I really wish I didn't have this photo in. Anyway, yeah, people know what hotels look like. Why have I got this photo? Also, it's a confusing photo, because I have to explain that there's only rooms down one side because of what the number line looks like. Really, this is the number line, but jazzed up a bit with this kind of hotel metaphor. Hotels don't have just one long corridor. What are we talking about? Anyway, here's the hotel. Here's what that looks like. There's a room number 1, a room number 2, a room number 3, a room number 4. It's the number line, but jazzed up with doors. I drew these doors in Microsoft Paint, not an art stream. Okay, so we've got door number 1, door number 2, door number 3, door number 4. The hotel is the same size as the set of all the positive whole numbers, strictly positive, because for every number there's a door, and for every door there's a number. Those are the doors we've got. There isn't a door 0, there isn't a door infinity symbol. There's nothing weird going on. There's other problems with doors that people in chat are now going to discuss. And a pun. Right, okay, good work, chat. This is a good support role here. Right, okay. So we've got all these doors, we've got these rooms. Here's what happens. Goodness me, the problem with preparing slides is I also have to remember what order they're in. There's even a TED video on something like this. I'm going to accelerate a bit. I'm going to skip some of the things in the TED talk. So here's the story that people tell. Hilbert is running this hotel. It's Hilbert's hotel. It's got all of these rooms in. Infinitely many rooms. That's pretty good. We're ready for people to turn up. Hilbert looks out of the window, and Hilbert realizes, disaster. Hilbert has double booked the entire hotel. So Hilbert looks out of the window, and I should say that in a world with infinite hotels, there are also infinite coaches, and 2 of them have arrived outside. Here are the infinite coaches that have arrived. Not an art stream. So these are the coaches. We're looking straight down on the coach. These are the sort of seats with the armrests. These are the headlights on the front of the coaches. I drew this in Microsoft Paint. There's a seat number 1, there's a seat number 2, a seat number 3, 4, 5, 6 on each of the coaches. These are infinite countable coaches, and both of them are full of people. Both of them have arrived at the hotel. Disaster, right? We've double booked the hotel. Okay. So, yeah, people saw this. It's the infinite hotel paradox, I think. And we can't tell if the goat is dead or right. Okay. In a finite world, before somebody in chat is probably going to tell us how to resolve this in a moment, but in a finite world, let's just stress, we're stuck now, right? If we've got 25 rooms and 2 coach loads of 25 people turn up and they're not allowed to share rooms, then we've got more people than rooms. We've got twice as many people as rooms, so we can't put them all in the hotel. But there's something we can do in the infinite world with an infinite coach. People in chat have been talking about shunting people down. So there's this strategy, just to give you a flavour of what things are like. If just 1 new person turns up after the hotel's full, if we overbook just a tiny bit by 1 extra person, then there's this thing we can do to move everyone down a room and put the new person in room 1. That's a sort of trick that I've seen some people say in chat already. For if 1 extra person turns up, then move everyone already in the hotel down 1. Put the new person in room 1. Pretty good trick. You can't do that with 25 rooms because the person will fall off the end. But with an infinite hotel, there's no end, so nobody falls off the end. We can't do exactly that here. We can't do exactly like that here. We can't take the first coach, put them in the hotel, and then tell them to shuffle down to make space for the second coach, because they'll have to shuffle very, very far and keep moving. So that's not really a solution, to put the first coach in and then tell them to shuffle and make space for the second coach, because if you put them in, then they're not getting sent to a new room after you've put them in if you shuffle them down infinitely many places. That's like telling them, you've got a room, and now please go to the end of the hotel that has no end. That's not really a solution. Okay, Josh in chat says that Josh has been to this talk in real life, but also fell asleep during it. So, told you it was boring. Right, okay, and people have got suggestions in chat, which I'm now going to okay. Yeah, here we go, just so we get some sense of how, there we go, about 10, 20 people, 20 people in chat have got, there we go, well done everyone. Wow, maybe doing a topic people have maybe seen before is not a good idea. Anyway, there's this solution which is amazing, which is to put one of the coaches into the rooms with odd numbers and the other coach into rooms with the even numbers, which is pretty amazing. And it works, right? Because everyone's given a sensible room number. Everyone's told, here's your room key. You're in room number 1, you're in room number 2, you're in room number 3, 4, 5. Nobody's told to go off down the end of the hotel that has no end. Everybody's given a sensible room. And it's sort of quite nice that, you know, you're exploiting the fact that the even numbers and the odd numbers both have kind of the same structure as the positive whole numbers. You just keep going. You can match them up with the seats on the coaches. Suggestion to build a second floor is also strong, I think. That's what hotels look like. Have mathematicians never been to hotels? Do we not know what hotels look like? Oh, well, never mind. So, yeah, okay, brilliant. You can even leave lots of rooms empty. Someone's got a separate plan for leaving rooms empty, which is, I think, showing off as well. If you can do it with also leaving some of the rooms empty. Maybe if you did something with multiples of 3, then you could fit people in and also leave some gaps. This is quite weird though, because what this shows, what the blue arrows at the top show, is the sort of surprising fact that the set of odd numbers is the same size as the set of positive numbers. Whole numbers everywhere. That's really weird. When I put the slide with same size on the board earlier, when I put that slide up of what does same size mean, it was pretty okay, right? You know, there's 1 to 1, so they're the same size. Here, the set of odd numbers is the same size as the set of all of the positive whole numbers, even though there's clearly twice as many, because we haven't quite defined clearly twice as many, but we have defined same size, and these things have turned out to be the same size. So that's a little bit strange. It's a little bit counterintuitive, I guess, that two things can be, one's clearly a subset of the other one, and they've turned out to be the same size. Yes. First list all of the numbers, like in the middle here in black, and then double them, and you get the even numbers. The even numbers are also the same size. That's a bit weird. Shivashi wants to put all of the odd prime numbers onto one of them. That's a sort of flex, right? To put the use the even numbers for one coach, and then put the odd prime numbers for these ones. This is just showing off because now you get lots of gaps. Okay, I like it. Style. I remembered to skip 9. We're doing good maths now. Yeah, using prime numbers, and I quite like this branch of mathematics because this kind of inventiveness about let's use the prime numbers, it actually works and actually gives you good ideas. Countable. They're not countable. These are countable. These are both countable. They're infinite, but countable. Because countable, let's be really careful. I also got away with something on the countable slide, which is boring. The countable slide just said, if there exists this one-to-one correspondence, it didn't say, I have to count them one at a time and spend actual time doing it. if I can describe that one-to-one correspondence, then I don't have to work out, I don't have to spend time going 1, 2, 3, 4, 5. I can, because we've got this nice rule or some idea that it matches up. We're going to be okay. Yeah, every whole number has an even number. Yeah, okay. Other sets that are the same size as the whole numbers, the set of prime numbers is the same size. The set of square numbers is the same size as the set of whole numbers, because I can square each number. That's some rule. So there's pretty lots of different things you can do to make a set that feels like it should be much smaller, but it's actually the same size as the set of whole numbers. What about the whole set of integers? So integers including negative numbers. Do you want to talk about negative numbers here? We can talk about negative numbers. So if I put positive numbers for one of the coaches and I have negative numbers on the other coach, then that's fine. I can, maybe, okay, let's imagine the hotel is actually the number line including negative numbers, but then disaster, we've got to move everyone out of the negative number side. We've remembered that negative numbers don't really exist or something, so we've got to move everyone out of that side of the hotel. That's fine. We can just put the positive numbers on one of the coaches, put the negative numbers on the other coach, and then do this plan to put them all back into the positive bit of the hotel. Maybe the negative half is closed for renovations or something. Okay, George wants to do something with a Fibonacci sequence without the first one, because the Fibonacci sequence has a repeat in it, doesn't it? So 1, 1, okay. Geometric theories joke here, very nice. Other things that you can count, yep, okay. If you use the odd primes, then it gets a bit tricky because you do have to work out odd primes. But I know that there's infinitely many of them. That's kind of the key thing, I suppose. I know that there is a millionth odd prime number. I know there is a billionth odd prime number. Working out what it is would be tricky, but luckily I don't have to actually do that calculation. Right, okay. Anybody, out of interest, anybody here not seen that before? Have I shown anything new to anybody yet? Half an hour in? We're going to try and speed up a tiny bit and get to stuff you haven't seen before. How are they the same size? Yeah. Oh, okay, we've got someone. Someone who maybe hasn't seen them before, right? How are they the same size when the difference between here is +1 and the difference here is +2? It's amazing. They're the same size because for each of these, there's one of those, and for each of those, there's one of these. They're in one-to-one correspondence. It's crazy. For each of these, there's one of those, for each of those, there's one of these. Just like with the 3 apples before, for each of these, there's one of those, for each of those, there's one of these. With the numbers and the even numbers, for each of these, there's one of those, and for each of those, there's one of these. They're the same size. An anonymous person hasn't seen it. Well, has... Okay. George has seen this before. Right, cool. Okay, right. I'm going to have to try harder to show you something you haven't seen before. Where are we going with this? More stuff? Yeah, okay. Have you seen this one? Okay, so, hotel's empty again. Everyone moves out. Hilbert looks out of the window and sees, oh no, I've really double booked myself this time. A countable infinity of coaches have arrived. So these are coaches, like the previous ones. There's a coach number 1, there's a coach number 2, a coach number 3, coach number 4, a coach number 5. They've got those signs in the window that say this is coach number 1, this is coach number 2, 3, 4, 5, and so on. There's a coach 37, there's a coach 1,000,005. I don't know if this is in the talk or not. Yeah, sorry, people have seen this one too. Okay, I'm going to give someone who hasn't seen this a chance to see this for a moment, and we'll accelerate. Okay, so the punchline for this one is that, maybe you've seen this coming, Hilbert's really overbooked himself, but he can still get everyone into the hotel. There's this way to get everyone into the hotel. So the one that people are suggesting in chat, oh Josh, it was in the talk, wasn't it? One in the chat, yeah, there's a couple coming up. One strategy is to walk through the seats like this. To start here, to go in diagonal lines, zipping backwards and forwards. Quite like this kind of geometrical approach like this. Handing out room keys as you go along. It's pretty good, I like that. And this way everyone gets a room key and no one gets sent to the same room as someone else, and just hand out all the room keys. This is pretty good with diagonal lines. Yeah, some people are saying map them to the nth prime to put them on prime powers. Maybe people who are thinking about primes before are still thinking about primes. So instead of that, you could send the first coach to powers of 2. Those are your room numbers: 16, 32, 64. Next one, powers of 3. I'm going to write down some of the powers of 3. And the next one, powers of 5, and use different primes. That's pretty clever, because then everyone gets sent to a different room as well. Maybe, okay, this is not so popular in number file videos or something. What if Hilbert looks out of the window and sees a 3D grid of coaches parked next to each other on like a multi-story car park, where each coach is countably long, there are a countable number of coaches, and they're stacked up in a countable kind of 3D grid. What do you want to do in that case? So I'm trying to describe a kind of 3D thing now. This is a 2D grid of coaches. What if there's a 3D grid of coaches? Of a 3D grid, so coaches parked next to each other, but also on every store of the multi-story car park that goes up to infinity. Yeah, people in coach numbers. Oh my word, right, okay. Cat's typed a bijection in chat. Yeah, that looks pretty good. That looks pretty good for the 2D thing. Different primes. Some sort of space filling fractal curve. Nth powers. Yeah, people want to do, even for the 3D version, people in chat want to do, maybe do a kind of cube space diagonal thing to kind of spiral around, I think. Oh, Pierre's actually going to link to the Veritasium video. Yeah, George's solution with multiples of 5 works if there's 5 coaches. I'm trying to think about what if there's like 6, 7, 8, 9, and so on. All of the numbers have a coach, so not just these 5, but more next to it. Your suggestion totally works for 5 coaches. Yeah, so if you could do for a 3D grid, for a 3D grid of people, you could do something in 2 steps, which I think is what Kat's describing, but I'll have a go. For a 3D grid of coaches, like a cube of people, you could, on each floor, you could reduce the 2D grid down to 1 coach, 1 hotel, with a method like the powers of primes that we just had, or the wiggly line through. So on each floor of the car park, you could reduce down the big grid of people down to just 1 coach. And then what have you got? Well, you've got 1 coach full of people on each floor. That looks like a square again. So you could go from 3D down to 2D by squashing everyone onto the first coach on each floor, and then go down to 1D by doing the same thing again. Go through doing the prime powers argument again, or the wiggly line argument, to squash down that 2D square down to 1D. And the next logical step, powers of primes in the previous part. First plane do 2 to each term. So there's 3 coordinates. Ooh, hello. People have got other formulas in chat as well. The logical next step is 4D coaches. And once you've had this idea about squashing down the dimensions to say, oh, this wiggly line or this prime power idea for 2D, actually that's a really powerful idea. That lets me squash down from higher dimensions to lower dimensions. So that if I've got a 37-dimensional grid of coach people space, then I can rearrange them using the prime power idea down to a 36-dimensional space and keep going and reduce them down to get them all into the hotel. So that even if I have a 100-dimensional grid of people like this, then I can use that idea about the wiggly line to reduce the dimensionality 1 step at a time on the way through. That's not in the number file video. Right, okay, ND, yep, good, okay. Powers was 2 to each term. 3 to, yeah, so 2 for, I'm worried about this powers of prime suggestion in chat. Because I think it's 2 to the power of, I don't know what each term means here. So if on each plane there's quite a lot of people because there's 2 coordinates on that plane. A little bit tricky. Here's the back seating and annoying. Chat's so funny. Can you do an infinite number of dimensions? That's not the same thing, which we're going to find out more about after Oh yeah, sorry. Was it an infinitely high 3D grid? Yes. Sorry. Everything infinite in all three directions. Ugh, crazy. Quite hard to think about. There's some sort of squashing going on where you can use that diagonal argument line. Okay. Right. I've got a couple more things to say that are maybe in the number file video. I desperately want to say some things that are not in the number file video. See if I can get there. Approach guy wants me to look at their answer, which I can't find anymore. Coach M will fill the rooms of powers of nth prime number. Yes. That passenger number is the power. Yes, that's the powers of... I tried to write down some powers on the screen. Yes, good idea. Height, oh hang on, also X is height over deck of coach N, nth coach's prime number and passenger number 2 to the power of X times N to the power of P. I think you run into trouble for the N equals 2 coach, or the N equals 4 coach. Oh, you give the coaches prime numbers and then do them to the power of passenger numbers. I think that might work. Yeah, okay. Well, I thought about that quite a lot. The squashing idea, so the squashing idea is just that this blue wiggly line for rearranging people into the hotel gives me a way to go from 2D to 1D. That's a terrible one. So it's like a way of squashing down the people from this 2D grid of people into a 1D hotel number line. And then if I have a 3D infinite grid of people, on each plane, on each level of the car park, I can use this trick to go from that 2D grid on that level of the car park down to 1D. It reduces the number of dimensions. So that instead of having this big 3D car park of people, on each level, I'm going to squash down from 2D to 1D like this. On each level, I've now got just one coach. So now that just one coach on each level is up the side of the car park. That's a 2D grid of people now. So I can use this to go. I can use this to go from 3D to 2D. I think I saw something. Kat said something like, if you think of this as some function of where you are, function of x and y, then if you have x, y, z, you can take that to function of x, y, comma z, or something like that. Too many brackets. Function of x, y, comma z, and then you can take that to function of x, y, comma z, another function or something like that. You can do the function twice. Right, okay. Ah, Matthew understood a thing. I think that's... Ah, brilliant, okay. When a prime's not odd, 2 is a very odd prime. Oh, I don't think 2 should be prime, right? Is that a theory that I've put forward before? Anyway, never mind. I think 2 should count. Yeah, people are now going to argue about whether 2 is a prime number or not. Brilliant, I love it. Right, okay, here's an ad break very quickly. I really want to say some things that Numberphile hasn't said. I know my video is much longer than a Numberphile video already, so what am I even doing? Ad breaks are always about adding. It's a break in the middle to do some adding. I guess there's this idea about if you've got two countable sets, so A is countable using the numbers 1, 2, 3, 4, 5, and B is countable also using the numbers 1, 2, 3, 4, 5. It's the same set as some set of same size as some set of positive whole numbers. Can you count both of them together? 2 is for context here. 2 is a very odd prime is not my joke. Somebody's put it as a quote. I'm quoting someone else. Do you want the 2 is not prime? So loads of facts in maths say odd prime. Loads of people say odd prime when if we ban 2 from being prime, then people can just say prime. Whenever they would say odd prime, they can just say prime if 2 is not a prime. And this is pretty nice because then all these things about odd primes that you see. So there's a fact like all primes are either one more than a multiple of 4, one less than a multiple of 4, or they're the number 2. That fact, if 2 is not a prime, would just be all primes are one more than a multiple of 4 or one less than a multiple of 4. Much nicer. If you ban 2, some things are a little bit nicer. You can't factorise even numbers if 2 is not prime. So that's a downside. But yeah, it's not a serious theory, in case anyone's wondering. Right, okay, good. Yeah, it does. Well, does it depend if the sets are infinite? I suppose for the ad break thing. Yeah, so Will's right. This is a joke on the 2 is not prime is a joke about whether 1 should be prime or not, right? It's all for convenience, right? So if it's convenient for 2 to not be a prime, then let's just ban 2 as well. I'm looking sideways at 3, to be honest. Right, okay. Matt Parker, actual Matt Parker, wants 2 and 3 to be smaller than all the composite numbers. Anyway, no, we like 2. It's not a okay. It's not a 2. Nobody's hating on 2. It's just like, I love the number 1, but it's not prime. I really like number 4, and that's one of the least prime numbers I can think of right now. It's the product of 2 not. But anyway. Right, okay. The answer to the ad break question is, sorry. The answer to the ad break, I'm so sorry. The answer to the ad break questions is yes. In the language of coaches, what you could do is put the items from A on one coach, put the items from B on the other coach, and then do the odd even trick. So take all your items, whatever they are, stick them on the 2 coaches that we had before. Those 2 coaches, we know how to put them in the hotel, do the odds evens trick. So yep, count them by putting them into the hotel. Now they're all nicely lined up with numbers. We counted them. So if 2 sets are countable, we can count the union of them. Even if they include repeats. You have to be a little bit careful about the repeats when you do the union, but whatever. Okay. 1 is... People are now going to argue about whether 1 is prime. Here we go. Right, okay. Okay. 1 not being prime is good because then you can say that none of the square numbers are prime. That's a good fact. I'm sort of joking. That's great. Right, okay. Oh, the odd even trick was the thing before where we put the items from A, they went onto the odd numbers. Remember we had those 2 coaches, and the items from B go onto the even numbers. So that's the kind of splitting things up thing. So put some of them on the odd numbers, some of them on the even numbers. So you counted each of them, so take your countable sets. Put them all on there. Okay. Right. People do... oh, right, okay, and people also... I thought this ad break meant the combinations, all of the combinations. Oh, yeah, put together is a bit of a weird... I should have phrased that different. What do I mean by that? What a weird phrase. Okay, the ad breaks are not always great. Yeah, so Charlie wants to know about repeats. If you've got repeats between the 2 coaches, then that's fine. You can just... you've got your repeated item, maybe it's on both coaches, and it's being sent to 2 different rooms. That's fine, just make sure that if it's given 2 room keys, that you take the smallest room key. Just put that in as a rule, that if I give you 2 room keys, then actually you just need to go to the smallest number that I've given you. So if you've got repeats, then you need to put in the extra rule that just says, oh, by the way, if there are repeats in the things that I'm putting in, I should only give them 1 room key. So if I accidentally give it multiple room keys, just take the smallest one. And that's a well-defined and nice way to make sure that it gets 1 room key. Right. Hey, is the root of all prime numbers except 1 irrational? Yes. The root of most numbers is irrational. Cool. Right, okay, good. Okay, right, more stuff. We've got another hotel problem. Have we got another hotel problem? Have I got more of these? Oh yeah, I've got more of these because I've still got to do more number file stuff. Oh no! I've got 15 minutes and I haven't said anything original. Except maybe that 2's not prime, which is maybe too original. Oh no! Right, okay. Maths Club, let's go. We're going to speedily do some more stuff. Here we go. We got the hotel again. And the story now is that Hilbert looks out of the window and finds, oh no, loads of guests have arrived for the hotel, and now the guests are snakes. And the snakes, in a world with infinite hotels and infinite coaches, the snakes are also infinitely long. We've got infinitely long snakes. And all the snakes are red and blue and stripy. The snakes have infinitely many stripes, countably infinitely many stripes along from the head down to forever. They don't have an end. And those stripes are either red or blue, or dark and lighter if you're red blue colourblind, sorry. The stripes are either red or blue, and for every possible stripe pattern, or not pattern, for every possible combination of stripes, there's a snake. What type of snakes? They're adders. We're not going to cut the snakes up. We're not going to do anything mean to the snakes. We're going to try and get them into the hotel. So let me just describe quickly how many snakes there are. Right, there are a lot of snakes. There's a snake that's entirely blue. There's a snake out there somewhere that's entirely red that needs to be given a different hotel room. There's a snake with just one red stripe in the 37th position, and all of the other stripes are blue. There's a snake with one blue stripe and loads of red stripes, and then another blue stripe really far along, much further along, 100th place is also a blue stripe. And there's a snake with stripes depending on the digits of pi. That's how many stripes of each colour it's got along its length. There are some really weirdly striped snakes, every combination of red and blue stripes, and they'd each like a room in Hilbert's hotel. Did I say that the root of most numbers is prime? I think I meant irrational if I said prime. Whoops. I'm going to rewind later. There is one snake for each pattern. Oh, this is also not original. I know. I'm trying to get there. And this is the really remarkable thing, that so far we've been really good at counting things, but this is too many snakes. This is too many snakes. We can't put them all into the hotel. To show you why, there's a very little proof. And this one feels quite different, because everything we've previously seen has been, we can count these things, put them in the hotel, here's a clever trick for putting them in the hotel. Here, this is too many snakes to put in the hotel. Somehow, even though the hotel has got infinitely many rooms, and infinitely many snakes have arrived, this is too many. Yeah, let me show you why. Yeah, okay, so the reasoning goes like this. Let's try and put them in the hotel, hand out number keys to each of them. Maybe we put this snake in, then this snake, then this one, then this one, in rooms 1, 2, 3, 4. If Hilbert tries to put the snakes in the hotel, then we can come along and build a new snake that's not in the hotel anywhere. A snake that hasn't been given a room. It works like this. If I work along the snake, so I look at the snake that Hilbert's put in the first room, and then I look at the snake that Hilbert's put in the second room, and I look at its second stripe. Then I look in the third room, and I look at the third stripe of the third snake, and then the fourth, and so on. I can build a snake that's different from all of those snakes by making sure that its stripe is different in the corresponding place. So this snake at the bottom doesn't have a number, because I've carefully built it to be different from the snake in room 1, different from the snake in room 2, different from the snake in room 3, and so on. So if Hilbert's put the snakes in the hotel, then there's a missing snake. That's a proof by contradiction. So we can't get all of the snakes into the hotel. They're uncountable, is the word. This is called Cantor's diagonal argument. More in the further reading, I guess. And it's really cool. Okay, right. Yeah. So I love this. Somebody's put in chat something really important that you can't shout during the number file video, but it is an important thing to say that people do say when I do this live. Can't Hilbert just shuffle people along? Shuffle the snakes along one room, put the new snake in, the missing one in, and then be done. And the answer is no, partly because we're going to run this argument again. Hilbert's got a new arrangement of snakes now. I'm going to recalculate and say, oh wait, sorry, you've got a new pattern down the diagonal, so actually you thought you were done, but now you've got this new snake that's missing. So Hilbert's got to do it again. And partly because we can run the argument again, and partly because Hilbert was supposed to be done. Hilbert was supposed to have put all of the snakes in the hotel, so it's kind of rude to be like, oh yeah, also I missed one. You can't have it both ways. Sort of already beat this. Yeah, people are arguing about binary numbers. There is no bijection between snakes and rooms. Okay. Yeah, the pattern of snakes. So this is a little proof that problem is almost to do with binary, I suppose. binary numbers going. There's some binary numbers going on. The snakes are secretly, they encode binary numbers more or less. People have spotted in chat that there's some repeats, so it's not quite the binary numbers. But there's a similar fact that the real numbers, things with a decimal expansion, decimal expansions are a bit like snakes, because it's a decimal expansion is a big long string of numbers that could be one of several things going on forever if you're looking at irrational numbers. Or rational numbers, they can go on forever, right? Especially if you write zeros at the end. Okay, so a real number can be written in decimal with digits to go on forever. And then you can run an argument like this to say, if you put those in a hotel, then there's something missing. So somehow there's more snakes than rooms. And this is an uncountable set of snakes. We can't count them, even if we use all of the numbers. Right, okay. Can we go one more? Yeah, so if they have 3 colours of stripes, then it's actually even easier to build the counterexample snake. Try it at home, I suppose. If there's 3 colours to choose from, then, well, that's even more snakes. So it's pretty bad for Hilbert. It's going to be great for us building the counterexample snake. Try it. Okay. Where am I going with this? So I want to do one last thing to convince you of something really weird in maths. I've got 9 minutes. I think it's in a Matt Parker video too, come to think of it. Right, okay. Works like this. Consider all words. I don't have slides for this bit. So I'm a mathematician. Words for me means any sequence of letters. So I consider this to be a word, not controversial. I consider this to be a word. I consider these also to be words. We're using some letters strung together. And okay, these are countable in quite a boring way. You can just count them because there's only a few letters that I could be using, and then only a few 2-digit. There's only sort of 26 of these right at the top, and then there's only 500 or so of these. So just list those next and just count them going through in order like that. So if I do that. If I do that, I can count all of the words. That's countable. Using 26 letters. And in fact, if I use 50 different letters, then there's not much difference. I would count all of the one letter words, then count all the 2-letter words, count all the 3-letter words, and then so on. Work your way upwards. That's countable. Oh my word. Number of snakes are the same. Ternary. Prime numbers. What if the first colour is red for all of the snakes? I think they're still uncountable. I think I can still build a counterexample. Fine, I'll make the first stripe red so that we're playing along with your rule, first stripe red, but then I'll build my counterexample snake after that. Will I know it's not the snake in room 1? I think, oh no, I'll shift along. I'll take the second stripe of the first snake and I'll build from there. So I'll just ignore all the red stripes. I'll count that as part of the head of the snake and then do the argument starting from the second stripe. Okay. Take all of the words beginning with A and remove the first A to get all the possible words again. Okay. So this is countable. In fact, even if I put lots of symbols in, so even if I put lots of symbols into my alphabet, then that's still countable. Something I wanted to put in here that I think is not in number file or Tom Scott video or whatever, is that even if the alphabet, even if you have a countable infinite alphabet, by the way, that's what the Unicode Consortium is trying to do. Unicode is this way of giving a number to every character, like snowman emoji has like some number that's been assigned to it, A has a number, even space has a number. So Unicode is this way of giving a number to every character. Let's say that they use up all of the numbers and they hand out numbers to every character, so that they've used up all of the counting numbers there are, all of the positive whole numbers. So we've got the countable infinite alphabet. Even if we do that, then the words are still countable. The 1-letter words are still countable because that's just the alphabet. All of the different emoji are in there now as well, and also all of this other stuff that Unicode have chucked in as well. Even if I have this countable infinity, that's countable. The 2-letter words, they're also countable, even if I've got infinitely many countable infinity of possibilities for each of the letters, that's still countable. That's the grid of buses that we have, the 2D grid. And in fact, these are also countable, the 3-letter words, because that's the 3D grid of buses. And then the set of these words is also countable. So I can count the 1-letter words, I can count the 2-letter words, I can count the 3-letter words. So then finally putting it all together, that's a countable union of countable sets again. So that's still countable. Some 26s in chats. I've moved on way beyond 26, so I'm behind. Yeah, so this is countable. I guess this is countable, but the snakes weren't. Each one of these, each word does have an end. The snakes didn't have ends. They kept going. Each word ends. So that is different. Okay. So yeah, so with ends in there as well from George, I've now gone from n to countable infinity. So if I have a countable infinite alphabet, then this is still countable. I can still count all of these things. So even if I use emoji, and also I use anything else that the Unicode Consortium could make up, then I still have a countable set of words, including space. So even if there's a Unicode character for space and for full stop. So even if I have a big paragraph of text, or everything I've said in the last hour, that's still a word under this definition, because that's just a string of characters, including space and full stop and comma and exclamation mark. That's just a string of characters, and each one of those is something from this countable infinite alphabet that Unicode have put together. Okay. That means that all the things that we can possibly describe using words and space, full stop and exclamation mark, and anything else like emoji in there as well, anything we can describe, that set of things is countable. So this is sort of like describable things. Countable. There are more snakes on one of the previous slides. There were more snakes on one of the previous slides than everything I can describe using a finite amount of text. That includes all the weird irrational numbers that you can think of. So all the ones that people have put as usernames, because your username is just a string of characters that I could pick out of Unicode. Each character is from a countable infinite alphabet. Those words are countable. So if your username is E, well, that's a description of a very complicated number, but it's just something in this big set of describable things. This big set of describable things is countable. And countable infinities, sort of the smallest sort of infinity. It's sort of the smallest sort of infinity. There's all these other interesting ones, like the size of the real numbers, or this big set of snakes. In some sense, most of the real numbers are completely indescribable. You can't describe them, even if you have like a computer program that calculates it. Then your computer program, guess what, is a word made of characters from this countable infinite alphabet of things that each character could be. So even if we invent lots of clever emoji for different things, then we can't describe all of the numbers that there are. Okay. Molly's fun maths fact of the week to wrap up with here. Today would have been Leibniz's 375th birthday. Happy birthday, Leibniz. That's Leibniz of calculus fame. If you want to find out more, then there is a Brief History of Mathematics podcast by Marcus de Sotoy. I remember that podcast, which is about Newton and Leibniz. There you go. Happy 375th birthday, Leibniz. Thank you, Molly, for the fun fact. The podcast series is also there by Marcus from Oxford. Okay. Cat thinks the set of all things we can describe is finite, possibly because Cat's not allowing me to have this really big alphabet of things. Yeah. If I'm allowed infinitely many symbols, like infinitely many different emoji that are listed in Unicode, then the set of things I can describe is infinitely big because I've got all of these different emoji. And that would be an infinite set, but still countable, because to get them on my phone, they've got to be in Unicode and they've got to have a number, like a positive whole number associated with each of them. That fact was pretty good, Molly. Good job. What's the one-to-one correspondence? So the one-to-one correspondence is quite tricky to describe because it involves lots of squashing, that operation that we mentioned before with the coaches. It goes like this. Find your description. So find your description in here on the left. Now, do that sort of... yeah, it's really tricky. Apply a very complicated function to it lots of times until you get down to a number. Yeah, apply a function to it where the function is quite tricky. It's the sort of squashing function for moving people around from a 2D grid to a 1D grid. Apply that lots of times, then apply the function one more time on the length that your original string was combined with what you just got. That gives you a unique answer. This is pretty unsatisfying in terms of what the correspondence actually is. This squashy function is really good. I guess I might try and put the squashing function into the further reading. This kind of magical function that takes a pair of whole numbers and gives you one whole number. So that whenever you give a different pair of numbers, you get a unique answer out. Okay, who's my favourite mathematician? I'm afraid it is probably Newton, which is, not a very exciting pick. Podcast link. Thanks, Molly. That looks legit as well. Right. Okay. Cat thinks the universe is discrete. Fair enough. Cat, they're making up new emoji every day. Maybe it's a stretch to say that they'll come up with infinitely many emoji, but maybe the universe is not big enough for that many concepts of emoji. Right. I think on that weird note, I think that's not in the Tom Scott video. Don't at me. Right. Okay. The link is not a Rickroll. Actually, it starts bbc.co.uk, but hey, what if the BBC uploaded some Rick Astley and then everyone links to it? That would be. Right, okay, why not? Why would it not be? Newton's great. Well, maybe Newton the person, not super great. Newton's mathematics, super great. Right, thanks to Athena. Okay, I'm going to wrap up the live stream there. I'll catch you for further reading at some point on the Maths Club website. I'm going to post that at some point tomorrow. Check out the weekend for more stuff about counting, including a squashing function. I think I've now promised to deliver that. And I'll see you in 167 hours for another episode of the Oxford Online Maths Club. Goodbye.